Okay, so first I wanted to go back to this problem from a second ago because just as we got cut off by the bell yesterday, we had a couple different answers that we got, right? We were trying to figure out what was this problem again. Was this the voting one? No, it was the medication one. So it was the medication one, and we were trying to find a confidence interval for, 95%. So we're 95% sure, so we're 90% sure of how many people this medicine's actually helping, what percentage of them. Okay? So they finally, in the last question that we were working on, they said, what sample size would we need so that we only have a 10% wide confidence interval, a pretty narrow one, pretty accurate or precise one, and that we're pretty darn sure about that, 98% sure. Okay? So we did that by, of course, plugging in 5% for the margin of error, getting this from our z-table, and using 27% as the approximator for our standard error. And then we just solve for n, right? So there's a couple different ways you can solve this equation for n. Yesterday, what did we do first as our first step? How did I get 0.0215 right here? Remind me. This should be easy algebra. Don't make this harder than it is. I divided. Yeah, I went 0.05 divided by 2.326. Let's do that again with our calculator. 0.05 divided by 2.326. You get 0.021496, etc. So I rounded it. That first rounding, since this is such a small number, is kind of dangerous. So it might have been better for me to keep some more decimal places here, like 4, 9, 6, 1307. That's exactly what my calculator told me. If you don't, I think you'll find your answers pretty different on this one at the end. Yeah, that's why we're getting differences. So rounding can have an issue. I'm going to show you how to do this so you can avoid that issue, but let's just do it first, okay? So we had that, and then what was the next step? How did I get rid of the square root? I squared it. So in my calculator, I'm just going to square that thing that's already in my calculator. And I got 4.62 e to the negative 4, which is 0.00042. And I have even a typo here. So this should have been 4620836 You can see I'm using as much precision as the calculator is giving me, so I can try to be real accurate and have no rounding errors, or not very much at all. Okay? And then the next step was I have an n on the bottom, so I multiplied both sides by n. So this number went down here. So I'm just going to copy and paste it down there. And then over here we just have this guy left, so in our calculator we say this divided by this. So I'm going to go 0.27 times 0.73, do that all divided by second answer with my graphing calculator. And my graphing calculator says 426.546. Which is what some of us got yesterday, and I think that was the people who were using like the second answer thing and pulling it down. The people who weren't doing that and were following my work exactly up here on the Word document got something pretty different. I think it was like 40 or 50 people different, so crazy. So that rounding had a big effect on this problem. That's because of the sizes, relative sizes of these numbers. So if you don't really want to worry about that as much, another way to solve this algebraically is what? Let me put another spot over here so we can do it side by side. Can you guys help me out? On that very first step, instead of dividing by 2.326, what could I do right away? I could square it right away. So if I square it right away, let's just keep it full precision. Let's not even use our calculator yet. Let's just write it down, shall we? You could go like this, right? And then square the other side. If you square the other side, you have to square the whole other side, right? So it's going to be that. And then the squared's going to cancel the square root. Of course, that's why we did it in the first place. So we'll have that. You guys got it? Then, if we want to get n by itself, what could we do next? We could multiply by n right now, or you could divide right now. Of course, algebra gives you lots of options, but if we want to make sure that we have no rounding errors, or very little, let's just multiply by n on both sides. So I'm just going to copy and paste this and put my n over there, right? And you can just delete it down here now. Uh-oh. Well, I'm just going to redo that. So times 0.27 times 0.73. We good? Okay. And now, the last step to get n by itself is divide by that thing that's being multiplied by it right here. So I'm just going to go like this. Well, you know what? I'm just going to say n. Oh, it's a different n now. N equals, and I'll have a fraction. And on top will be all this stuff. And on bottom will be 0.05 squared. You guys got me? Stick that in your calculator. Just do me a favor. And make sure that you get the same answer that we did. I'm going to do it too. So in my calculator, I'm going to try this out. Squared times 0.27. And this is pretty easy to put in your calculator, honestly, I think. 0.05 squared. And what do you get? I think you should get the same answer. You'll get this guy. And notice, was there any opportunity for me to have any rounding error in there? No, because I never even touched my calculator until the end. Now, I don't care how you do these, but if you're going to do it, be careful about keeping as much precision as you can throughout the calculation. Okay? So, I thought it was good to look at that one more time. Let's look at number 3. Number 3 says, what sample size does it take to estimate the outcome of an election with a margin of error of 3%? So this is just a new question, right? New question. Margin of error of 3%. I think there's some assumptions we have to make about this problem. We won't go through the formal assumptions, but it's just like this last one, right? We're going to have a calculation just like right here. So I think first of all, did they demand a confidence level? No. You said 95%? Okay, let's go 95%. So we are going to choose a 95% level of confidence because that's the most common one. You're right, Brandon. You should always go for 95 or 99 depending on how sure you want to be. Since they did not specify. Okay. Alright, that means what is Z star going to be? I know Z star then is, you guys tell me from yesterday if you remember or look it up again. 1.960, yes sir. So Z star is 1.960. Yep. I'm going to unbold this because it's freaking me out. Go over here, there we go. Alright, so we know that, so we know our margin of error formula for a single proportion. Now if we were doing a single mean confidence interval, it would be a little different, but the theory would all be the same. If we were doing something else with double proportion, like we'll do soon, theory is all the same, the formula is just slightly different, it's even on the AP test. I mean, changing the kind of interval doesn't change anything else really, so we'll be doing lots of different ones. So we put, they only want it to be 3% wide each way, right? So we say that equals this times our standard error, which is going to be the width. So I'm going to put, I'm going to write this one more time. Like this, 0.03 equals 1.96 times square root. And then, what are we going to use for P and Q and N? Well, N we're looking for, right? So maybe I should have said that up here. N equals what, right? Go lowercase. That's what we're searching for. P and Q, do we have any information? This is just some random election that we're trying to estimate. What do you guys think? We got to make some kind of guess at what P and Q would be. This is just a random election. How can we guess anything? Elections are pretty close usually. Now that's not necessarily true in Europe in some places and stuff. But if we want to be as conservative as possible because we want to make sure that we pick enough people so that we have what we want, right? So we have 95% confidence and we have a margin of error of only 3% each way, we better be conservative with what P is. So what's the most conservative possible P? 50%. Does that make sense? 50-50. Yeah, so we're being extra conservative here, so we'll make sure we have enough people. I guess we're not being very conservation-wise with N, but that's okay. We're just sending out surveys, it's cheap. So we'll go 0.5 times, 0.5, and divide that by N, come on. Yes! I'm sorry, I get excited when I get Equation Editor to work the first try. Okay, so you guys tell me which way do you want to solve this? We just solved it, one just like it. Should we do it the second way? I think that was a little better. So, then I should do what first? Tyler told us last time. Somebody else tell me this time. Square it. So we're going to square both sides. All of both sides. Which means the square root will cancel and we'll just have... Oh, come on. This part? Yay. Haha. Okay, well, it's 0. There we go. And then we're going to multiply n on both sides. So we'll go like... I'm going to go like this. So now n goes up here. 0.5 times 0.5. And the last step will be divide that other thing to the other side. So let's say n equals that stuff all divided by 0.03 squared. And what do we get? No, stay big. What'd you guys get? 1067 point. So what are we going to say? So we conclude we will need at least 1,068 people to achieve a confidence level of 95% and a width of 3% in either direction for our confidence interval.
Would we want to say about 1,068 people because we estimated 0.5?
You're good question, Carson. So I said at least there, right? You definitely don't want to go less. But yeah, I could put a caveat on there like John is saying and say, assuming the true population value of people voting for whatever candidate is 50%. Now, of course, if it's less than 50% or more than 50%, I think we're covered because we were like the most conservative we could possibly be. If it's like a lot more than 50%, we're going to catch it no matter what. If it's really close, we've got at least enough to be able to tell. Now, of course, is this a sure thing still? No, it's just a confidence interval. It's got 6% wide. We might not capture the true thing in that net. That's why polls are not certain. That's why everybody thought Trump was going to lose this election. This is exactly like that situation from this year. And what happened? He didn't. So there was something flawed about the polls, either from a conspiracy point of view, if you want to go for that, or from a confidence interval just didn't do it. Or maybe they didn't pick enough people in their polls. Does that make sense to you guys? Okay. So polls are not perfect. Let's look at one last question and then look at the simulator. So I wanted to look at that one I just gave you. So we're going to do one with a mean. So go ahead and read this guy. So you're watching the little tape here. You want to read this guy first, maybe pause it. Oh, can I get you, Tyler? I'm sorry. Yeah. I want you to read this example on the top of homework 2. It says the paper, this is one I looked up, like I found it on the internet back in the day, about 4 years ago. It's a medical journal. This is the kind of stuff you got to be able to read, even if you're, I was bad-mouthing psychology majors the other day. I felt kind of bad about that afterwards, because there's a lot of really good psychology majors out there. That's just something that people say in college, which is generally accurate. Anyway, psychology majors use this class probably more than any other major, honestly. They use statistics heavily. So anyway, this is a paper from psychiatrics, I think, which is not the same as psychology. Let's be clear on that, too. The paper Mean Platelet Volume in Patients with Metabolic Syndrome and in its relationship with coronary artery disease includes data that suggests the distribution of blood platelet volume for patients who do not have this metabolic syndrome, which is a combination of factors indicating high risk for heart disease, is approximately normal. And it has a standard deviation of 0.75. They're so generous to give us that 0.75 thing. Suppose we have a sample of 40 patients and have recorded a mean blood platelet volume. This is the kind of test you take when they're assessing you for heart disease if you're going into, because you're worried about a heart attack or if you have chest pain. This would be one of the tests they'd run, a blood platelet test. And the mean for those 40 patients comes out to be 9 units, whatever that is, okay? Estimate the population mean with a 99% confidence interval so that you can figure out what that population mean was supposed to be for everybody, okay? So I had a little note here. I said it is actually extremely rare to know the sigma as we did here, in other words, that 0.75 number, but we'll learn how to deal with that in the next chapter, okay? If you don't, you can no longer use the Z procedures that we've been using. So this problem is one where you do know it, and your problems in your homework, you know it as well. So we'll address this in probably not a few weeks, 1 or 2 weeks, I think. So what do you guys think? Before we go about constructing our mean confidence interval, what should we do first? Check your assumptions. Right? And what would you say, Montana? Yeah, right, yeah, good. Yes, gotcha. Okay. So generally, yesterday, what was the first general assumption that you should always check? Independence. We still want to do that if we're doing means. So how do we do that if we're doing means? Well, we want to think about 2 things to check independence if we're doing means. We want to look at randomization, just like last time. So you guys tell me. Randomly collected, what did we do here? Did we see anything about random? That's not with random, though. It says, suppose we have a sample of 40 patients and have recorded a mean blood platelet. They didn't tell us anything about random, so we're just going to have to say, assume these patients were measured or collected, whatever, measured randomly with an SRS caution, because we don't know that. The other thing we need to do to check to establish independence is if these 2 things are met, which the first one's already iffy, but okay, we'll assume they did that. They're researchers. Come on, they don't do things randomly. 10%, what do you guys think? What should I say here? Population of people. What is the population of interest on this problem? Who are we looking at? Is it real specific? Let's go read it one more time. Yeah, I think it's specific. McKinsey's right. Blood platelet volume for patients who do not have a metabolic syndrome. That's it, right there. The population of people without a metabolic syndrome. So normal people, kind of, right? Is definitely, I'm feeling comfortable about this one, aren't you? It's definitely more than Jamie said, 400. That one's definitely good. We're good to go there. So we're probably independent. The other thing we need to do is check normality. There's no NP and NQ because there's no P and Q. This is not a proportion problem. So how do we check normality for a mean problem? We either have to have a sample size of more than 30, so the central limit theorem kicks in, or they just have to tell us. How about this problem? We're good on both counts, right? They said the population is right there. They said the population is approximately normal, and we also have more than 30, so we're definitely good to go to use z-scores, okay? So let's put that down here. Normality, make it bold. Since we have a sample of 40, the central limit theorem says the sampling distribution, and you want to write this out very precisely so you're understanding it, of x bar is approximately normal, which by the problem explicitly told us anyway. If either one of those two things was there, you'd be good to go. Okay? So we're definitely good to create this. The only issue is the randomization, but I think we're good on that one too. So confidence interval. I think this was in your guide. Can you guys help me out? What's the center of this confidence interval going to be? It's not p hat. What's the statistic that we're collecting? X bar. I have trouble writing X bar, so I'll do it. Okay, I'll do it just for you guys. There we go. X bar. Now what? Plus or minus? Plus or minus what? This is just like the other one. What comes next? Z star. So we're still using normal stuff, right? We don't have a T star yet. Z star, and then this is, what's the standard error for means? Sigma. You guys see that magic? I gotta do one more time. Sigma is spelled like this. Divided by square root of n. There we go. That looks pretty good. Yeah? I usually put the Z star in front, but that's still valid. There we go. So there's the formula. We just got to do it. All right. Our confidence interval is going to be... What was X bar? Did they tell us? I hope. 9. Plus or minus. Z star, what were we going? 99%? Can you guys remind me what's 99%? 2.576. Okay. Times. Let me put a fraction in here. We knew the standard deviation, right? It was 0.75 and square root of 40. So why don't you guys go ahead and calculate that confidence interval. Go like this and give me the two edges. So go with the low one and the high one. I really don't have it here. You guys are going to have to tell me. Oh, and I had some units here, by the way. I put fluid ounces. I kind of made that one up. I forget what their measurement was, so we'll just use fluid ounces. That's probably way too much for platelets, but yeah, I'm making that up. I'm not a doctor, sorry. What'd you guys get for the lower bound? Say again, John. 8.695. You guys have confirmation on that? Okay, and the upper bound's probably like 9 something then, right? 9.305 confirmation? Okay, there we go. Interpretation. We are 99% confident that the... You guys got to help me. I put that in there just to remind you what the true mean symbol is. Of people who do not have a metabolic issue is between those two numbers, 8.695. Make sure you get your units on here. That's why I put them there. Fluid ounces and 9.305 fluid ounces. There you go. Done. That's what they wanted to know. Okay. So there we go. We estimated what the real average number of platelets is for peoples. Okay. Let's look at a simulation here real quick before we call it good for today. I'm going to save this. So this is actually on Moodle if you want to play around with it, but I'm just going to pull it up. So I put this on Moodle. It's a confidence interval simulator. So I think we can look at simulations of what we've been talking about. So let's pretend the true population proportion, we can make it whatever we want. This is a proportion one, unlike the mean one we've been doing. So if we want to say the real proportion of people who have yellow as their favorite color, if it's really 20% of people in the world, and we want to use an 80% confidence interval, in other words, a real rough one, and we start out with samples, we go and survey people and ask them what their favorite color is, and we ask, let's go real nice and small, 30 people at a time. Why do you think they stopped with 30 here? The central limit theorem, yeah. So let's draw one sample at a time. Now, one sample is going to yield how many confidence intervals? Well, one, right? So there's the real thing, right? Can you see it in green right there? Are we going to capture it? Are we going to capture it? Yes, we captured it. See it? It's in there. See how the green is in the interval? Good to go. 1 out of 1. Another sample. Right on. Look at that. Right in the middle. 2 for 2. 3 for 3. 4 for 4. Oh, we missed one. So is it possible to miss one? If you pick 80% confidence, how often, approximately, are you going to miss one? 20% of the time. So it depends how important it is that you capture the true thing. Remember, this is godly knowledge. In real situations, you don't know this, and you're using this interval to estimate it. But if you use 80% confidence, you're only 80% confident that you caught it in your net. Like, it's caught here, right? It's in the net. In the net, in the net, in the net, in the net, out of the net. We missed it. So this is a really bad situation to have right here. So if you're really worried about that happening, what do? Increase the confidence, or you could increase the sample size. Let's do that in a second. But let's look at the long run. It's supposed to be 80% in the long run. So far, what's our percentage? 87. As I keep pushing this button, watch what happens to that number. Oh, man. It won't go exactly down towards 80% exactly. There's random variation, right? But in the long run, it should get pretty close to 80%. It'll go up and down, but it's going to narrow in. Now, I'm just going to send 25 at a time since it's jumping around on my screen. Look how close it got once you get to 37 samples. 81%. Now, if I hit 25, is it for sure deterministically going to get closer to 80%? No, but it's more likely to happen, right? So let's see what happens. I don't know. It's closer. Now see it bent down a little bit. So that last 25, look how many errors we have. Look how many times we missed the butterfly. We missed it a lot of times in that last one. That can happen due to random variation. But in the long run, it's going to keep creeping back towards 80%. Do you guys see that? Now, we said we could increase the confidence level. If I increase the confidence level and leave everything else alone and just do one sample at a time, is my interval going to be wider or narrower than last time? More confidence means wider interval. Look at that. See how it's wider? If I go more confidence, wider interval. You guys see it? And in fact, if I move this up here, you'll really be able to see it. Watch how wide this is. See how wide it is? So if you're 99% confident, let's go back to 80% just to get back to where we were. So we're back to 80%. The real thing is now at 0.36. That's the real thing. You guys said we could increase the confidence, or we can increase the sample size and leave the confidence alone. And that's going to help us, right? Increasing the sample size that much, what did it do? It shrunk that down and makes it real tight around the real thing. So we're probably going to get it most of the time now. Watch. I'm going to hit sample 25. Sample 25. We're still missing it, but at least we're pretty accurate. Notice, even if we miss it now, because how often are we going to miss it? Look at my settings. The way I have it right now, I'm going to miss it 20% of the time. That's a pretty fair number of times I'm going to miss it. But even if I miss it now, since I have such a large sample size, aren't I really close every time because of how thin those confidence intervals are? So this is the give and take that you've got to work with in statistics, in inference in general, that we're going to be working with the whole rest of this semester. So this is a neat little applet. If you want to investigate it, have some fun with it. It's pretty fun. All right. I think we're good to go. We're going to stop there for today.